underperforming on standard image classification benchmarks, SIGLET-based Pali shows superior performance across various multimodal benchmarks, especially on localization and text understanding. The SIGLET encoder we use is a scaled-up version using 2 billion parameters and achieves a new state-of-the-art on multimodal cross-modal retrieval. We consider that Pali 3, at only 5 billion parameters, rekindles research on fundamental pieces of the complex VLMs and could fuel a new generation of scaled-up models. Introduction. Scaling of vision models VLMs to tens or even hundreds of billions of parameters has shown ever-increasing performance. Meanwhile, models at a smaller scale remain critical as they are more practical to train and serve, more environmentally friendly, and support faster research cycles for model design. In the spirit of focusing on smaller scale modeling, we present Pali 3, a third-generation family of Pali models. Using a pre-trained backbone with only 5 billion total parameters, we refine the training recipe and achieve competitive and new state-of-the-art SOTA results on various VLM benchmarks. Our new recipe has 3 main components: contrastive pre-training of image encoder on web-scale image text data, and improved data set mixture for Pali multimodal training and training at high resolutions. Pali 3 achieves new SOTA results on tasks that require visually situated text understanding and object localization, including 8 visually situated text understanding tasks and the referring expression segmented task of ref COCO, along with a strong performance on the wide range of classical vision tasks. As part of this work, we introduced a SOTA multilingual contrastive visual model scaled up to 2 billion parameters, obtained using the recent introduced SIGLET recipe. Additionally, we performed focused tabulation studies to compare the classification pre-trained vision transformer with it backbones with the contrastively pre-trained ones, SIGLET. This further confirms the viability of pre-trained visual encoders on noisy web-scale image text data as a preferable alternative to training the classification style data. Our contributions summarized as follows. We compare classification pre-trained bit models to contrastively pre-trained SIGLET models using the Pali framework. We find that the contrastive pre-trained models work significantly better for visual situated text understanding tasks and localization tasks. Our model achieves SOTA performance on 10 plus diverse vision language benchmarks, while being 10 times smaller in size compared to the current SOTA model. For understanding visual situated text, the improvement is by a particular large margin. By not pre-training any of the video data, our model achieves new SOTA on several video QA benchmarks, indicating a powerful generalization abilities. We introduced the 2 billion parameter VIT-G multilingual SIGLET model trained on WebL, which sets a new state-of-the-art multilingual cross-modal retrieval benchmark across 36 languages. Related work. Recent large language models, VLMs, use pre-trained image encoders as part of the large model, and some pre-train it with vision classifications. PolyX, Flamingo, Pali. Some use pre-trained clip encoders, cross TVR, TrackBridge, and some with custom multimodal pre-training, COCO, SimVL. In this paper, we compare 2 dominant ways to pre-train image encoders using the Pali framework. Classification pre-training using large, weakly labeled data sets, and contrastive pre-training on a web scale with noisy data. A recent finding spanning across Pali and PolyX is that scaling up the classification pre-trained image encoder seems more promising than was previously believed, especially while classic image-only benchmarks such as ImageNet seem to indicate saturating performance for scaling pre-training of image-only models. Only shows that by scaling up the vision encoder from bit G to bit E, the improvements on the VL tasks are more noticeable than on the ImageNet. PolyX further scaled up both the vision language models, showing that these larger image encoders keep bringing benefits when plugged into large VLMs. This finding suggests that there is more to be found regarding the pre-training of image encoders in the context of VLMs, which may lead to different conclusions when looking at the VLM task as compared to a pure vision. In this paper, we dive into the impact of the image encoder for the VLMs by directly comparing classification pre-trained vision models to contrastively pre-trained ones, and revealed that the latter are vastly superior for a variety of tasks, especially localization and vision-situated text understanding. We can split multimodal understanding capabilities into two categories: natural scene understanding, captioning, QA, object detection and localization, and vision-situated text understanding, documents, infographics, QA. These groups of tasks require different granular understanding, and previous VLMs have largely focused on one type of task, leading to their pre-training recipes being attuned to that type of task. For example, Pali 17 billion and PIC2Struct showed strong performance only on one of the two categories, respectively. The recent PolyX achieved SOTA performance on both categories based on an improved OCR-related training recipe and a significantly larger 55 billion parameter model. In this work, we combined the advantage of contrastively pre-trained bit and further improve and balance training recipe into Poly 3, demonstrate that SOTA level performance on both the categories of multimodal understanding is achievable even at 50 billion parameter scale. Architecture. On a high level, the architecture follows Chen's, and a bit encodes the model into tokens, which together with the text input, the question prompt instruction, are passed into the encoder-decoder transformer that generates the text output. So here in figure 1 is an overview of Poly 3 5 billion model. Images are decoded into visual tokens individually by the contrastive pre-trained 2 billion siglet vision model. Along with the queries, these visual tokens are passed to the 3 billion encoder-decoder UL2 transformer, which produces the desired answer. In such a setup, a contrastive pre-trained model provides significantly more useful tokens than one classification pre-trained model, as in the previous Pali models. Here, where's the photograph for resting? And then that's sent to the tokenizer. And then this would be the encoder-decoder. And so it's also at the same time taking in the image with the contrastive vision encoder.
The green and purple blocks are the embeddings. So you see the output of VITs and the output of the text, they're completely different, but this here, what you're looking at, this is where they're combined. This is how the model actually understands the vision and the language at the same time. They're still different, but the model can still perceive them in a unified and interconnected fashion.
Okay.
So that's how the model knows that they're different tokens, but it also can see the whole picture, not just the text or just the image. It understands the differences between the two modalities, but it also understands the interconnectedness of both modalities. So that's why it says, where is the photographer resting? In a hammock under a tree on a tropical bench. So it would have to know both where is the photographer resting in text. It would have to know what that means. And it would also have to understand the image. It would have to see there's a beach, there's feet. What are feet? What are humans? And then what is the beach? What is a rock? What is a hammock? It would have to know these things. And so the contrastive vision encoder is the VIT. If they say that, just think of a VIT. So the VIT will output the vision tokens, the visual tokens, and then they'll be concatenated. If we go down a little bit, we'll see what happens. Um, oh, oh, oh. Images are encoded in the vision tokens individually by the VIT model. Along with a query, these visual tokens are passed through a 3 billion encoder decoder UL2 transformer, which produces the desired answer. In such a setup, a contrastively pre-trained model provides significantly more useful tokens than the one classification pre-trained, as in previous Pali models. So contrastively pre-trained models are different than classification. Evelyn, do you know the difference?
I haven't been paying that close attention. I'm sorry.
I see. Dimitri, would you know the difference between a contrastive and classification model?
I think contrastive encoders are usually done on pairs, and they're sort of there's like a positive sample and a negative sample, and they sort of like the positive sample pushes one way and the negative sample pushes the other way. I'm not explaining it very well, but yeah, I think it's a pairwise kind of objective, but I don't know if that's what they mean here.
I see. How do we explain contrastive? I'm looking for a diagram. All right, let's just keep going.
Visual component. The visual backbone of Poly 3 is initialized from a contrastive pre-trained VIT model using the Sigler training recipe. In short, an image embedding VIT model and text embedding transformer are trained to separately embed images and text using that, such that a binary classifier such as the sigmoid cross entropy of the dot product of the image and the text embeddings correctly classifies whether the respective image and text correspond to each other or not. This is somewhere to click in the line, but was shown to be more efficient, scalable, and robust. And this is done in order to pre-train the VIT image embedding component. Hence, the text embedding transformer is discarded when inserting to the VIT into the Poly.
Wait, can we go back? Just hold on for a sec. An image embedding by VIT and a text embedding transformer are trained to separately embed images and text such that a binary classifier uses the sigmoid cross entropy of the dot product of image and text bidding, which correctly classifies whether the respective image and text correspond to each other or not. So this is what I was talking about. This is how it understands the cross modality reasoning. This is how it's able to understand what the image is and what the text is at the same time, which is similar to clip and align, but shouldn't be more efficient, scalable, or robust. So they pre-chain the VIT image embedding component, and hence the text embedding transformer is discarded when inserting the VIT in the Pali. All right, let's continue.
The full Pali model. The outputs of the bit image encoder before the pooling form the visual tokens, which are linearly projected and prepended to the embedded input tokens. Together, these tokens are passed into the pre-trained 3 billion parameter UL2 encoder-decoder language, which generates text output. The text input to the model typically consists of a prompt that describes the type of task. That generate the alt text captioning tasks and encode necessary textual input for the task, answer and lane, and the question for the QA task. Stage of training. The training procedure is similar to Pali and PolyX and consists of multiple stages. Stage 0, unimodal pre-training. The image encoder is pre-trained contrastively on image text variants from the web. Following the Stiglet training protocol, this differs from the Pali and PolyX, where the GFT classification pre-trained encoder was used. We use a model-based filtering approach similar to that in Scumanham that retains about 40% of the pairs. The image encoder is trained at a resolution of 224 by 224. The text encoder-decoder is a 3 billion UL2 model trained following the mixture of denoiser procedures described by Tay. The multimodal training. Here the image encoder is combined with the text encoder-decoder as described earlier in Figure 1. Then this combines the Pali model is trained on a multimodal task and data mixture, albeit keeping the image encoder frozen and using its native resolution. The main mixture component is again derived from the WebLI dataset by heuristic filtering of the text quality using the split cap training objective. Further ingredients inherit from our multimodal captioning on the CC3M35L and the WebLI OCR cross-label BQA and BQG using BQ-ACCML35 objective-aware QA, as well as object detection. Notably, we do not include task or data derived from the video. This was done in PolyX. Poly 3 retains competitive performance on these benchmarks thanks to its strong image encoder. We do, however, further improve the document and text understanding capabilities by enriching WebLI with PDF documents with dense text and web images described as posters or documents in 100 languages. Resolution increase. High resolution input is a widely accepted way of increasing performance due to making more details from the image perceivable and due to increasing the model's power via increased sequence length. We increase Poly 3's resolution by fine-tuning the whole model, unfreezing the model decoder with a short circulum of increased resolutions, keeping checkpoints of 812 by 812, 1064 to 1064 resolution. The data mixture focuses on the part that involves visually situated text and object detection. Task specification transfer. Finally, for each individual task, we fine-tune the Poly 3 model with the frozen bit image encoder on the task training data as described in the corresponding section. For most tasks, we fine-tune the 12 812 by 812 resolution checkpoint. But for 2 document understanding tasks, we go up to 164 resolution. Experiments, classification or contrastively pre-trained bit. We performed a controlled comparison of different bit models within the Pali framework. We consider 2 types of bit models: classification, pre-trained, class if on the GIFT dataset, contrastively pre-trained on the WebLI dataset. We perform these experiments using the fixed 224 resolution, i.e. only includes stage 1 to save compute. We further shorten the stage phase to 20% of the full Poly 3 schedule used in the remainder of this paper. The results in Table 1 painted a clear picture overall, while the few-shot linear classification of SIGLIP models falls behind. When used in Poly 3, SIGLIP models provide moderate gains on simpler tasks such as captioning and question answering, and large gains for more complicated scene text spatial understanding tasks such as text VQA and RefCoco. Table 3 results on benchmark are more focused on understanding visual situated text. Text caps, text QA, STD QA, infograph VQA, and doc VQA are all evaluated using corresponding official evaluations. Methods marked by that symbol are trained on additional VQA data similar to this target benchmark for fine-tuning the target benchmark. For chart QA, we compare with the similar steps for fine-tuning without chain of thought or similar prompting techniques. SOTA models variance, and this motivates the departure from the classification pre-training image encoders and switching to sigmoid contrastively pre-trained ones for building Poly 3. Visual situated text understanding. We evaluate Poly 3 on visually situated text understanding tasks, text caps, and infograph .qa. The images in these datasets span a wide range of domains such as natural language, illustrations, documents, and user inference. For infograph VQA, we don't really need to read that. Averaging over 8 benchmarks in Table 2, we result in all settings. Poly 3 is only 0.7% of all SOTA methods combined with the settings where external OCR settings were used. However, the setting without such external system Poly has a significant 4.4 point advantage over all SOTA methods combined for text cap, VQA, and VQA is 8 or more points. Finally, we see that Poly 3 without any external OCR system is only 1.8 point behind relying on one, suggesting that image encoders are strong intrinsic OCR capable. Preferring expressive segmentation. We extend Poly 3 with the capability to predict segmentation masks via language-like input. To this end, we make use of the vector quantized variational autoencoder. And the VQA is trained to learn a discrete code block of 128 mask tokens. The encoder can tokenize a 64 by 54 pixel segmentation mask into 16 mask tokens, which the decoder can convert back. We train Poly 3 to predict a single segmentation mask. First, Poly 3 outputs full coordinates of text representing a bounding box, and this is followed by 16 mask tokens that represent the mask inside the funny box. We fine-tune Poly 3 on the combined training set of Riff Coco. Each training example consists of referring expressions and box segment mask. We prompt Poly with my prompt. Type the brown dot on the left, and the target is a sequence like that, and when the target sequence contains 16 maps tokens between 0 and 127 that are generated by the VQ AE encoder using the segmentation mask. The results in Table 1 demonstrate the contrastive pre-training of the more effective classification of class type. Natural image understanding. In this section, we evaluate Poly 3 on general image understanding tasks, which target general visual understanding focused on knowledge understanding, which measures performance on counting under textual guidance. All results of the benchmarks presented in Table 4 using 812 resolution. As in previous work, we employ a no external OCR model since these benchmarks rarely involve text in the image. Overall, Poly 3 shows very strong performance on these benchmarks, despite being much smaller. Video captioning and question understanding. We fine-tune and evaluate Poly 3 on 4 video captioning benchmarks. The brief description of each benchmark is provided in Appendix A. Following the setup of Poly X, we fine-tune our models, and we sample the 16 frames with a fixed temporal stride for each benchmark. Each frame is independently processed by the image encoder. The resulting visual models are simply concatenated, leading up to 496 visual tokens. The key difference from Poly X setup is that there is no video data in the Poly 3 pre-training, meaning Poly 3 has never seen multi-frame inputs during pre-training. Table 4 is the results. The underscored numbers indicate Poly 3 is behind. This is just a comparison between those models for video captioning. And then Table 5 is the video captioning and video QA, with those compared on those models. And despite not being pre-trained with video data, Poly 3 achieves excellent video QA results with smaller model size. New state-of-the-art performance on the MSR, QA, activity net QA, and competitive results on the net QA. The consistent improvements on the image and video QA highlight the benefits of adopting the contrastive bit. Poly also achieves respective video captioning results, underperforming the SOTA by only 3 points on average, considering the model size. Poly 3 appears to be an excellent choice in terms of both performance and practicality. Evaluations of the visual components in isolation. We fine-tune classification accuracy on the image net, and this is the classification across the 8 tasks. And here are the statistics generated. And the caption statistics generated. Direct image encoder evaluation. Here we aim to directly evaluate the learned image encoder without the surrounding language model. i.e. the full Pali 3. All results are summarized in table segments. First, we test the image classification capabilities using the standard ImageNet benchmark and two of its most popular variants. We fine-tune the unimodal image encoder from stage 0 on the ImageNet and compare it to fine-tuning classification pre-trained bits using the previous Pali models. The main comparison is to the classification classif pre-trained on bit. The SIGLET slightly lags behind in terms of accuracy, but matches in terms of real accuracy. And the metric which avoids measuring overfitting for ImageNet particularities. Second, we report multilingual image text retrieval results on the cross-modal 3600 benchmark. Once classification pre-trained image encoders have this capability, we use low-tune text encoder for it on the multilingual WebL dataset. We also use LitTune on a text encoder for the SIGLET image encoder in the exact same setting to remove any confounders from the comparison. The SIGLET bit model clearly outperforms the classification pre-trained bit model. Finally, we perform linear probing on the representation in a few shot settings following the Bazitsky across 8 different classification tasks used in the VI report to the average performance. Here we see SIGLETs lag behind, likely caused by the representation is not pre-trained in a way that supports linear separability as recently uncovered. Dutchman. Taken together, these results paint a clear picture. The best of the largest classification pre-trained image encoders appear slightly better when evaluated on standard classification tasks. However, they are slightly worse than the SIGLET pre-trained image encoders for vision language tasks. Model fairness, biases, and other potential issues. We follow the evaluation protocol to access the model fairness and biases and other potential issues. We use the MIPE datasets to generate captions and use the Perspective API to measure toxicity and profanity among other potential issues and summarize the results. The results are comparable to those in PolyX. Table 9 is the detection error rate for person that contains on the data set that contains exactly a single individual in the image and maintains lower error rate across the subgroups. Skin tone follows the Monk scale, skin tone scale, and numbers inside the square brackets correspond to the size of each bracket. Yeah. Level of demographic purity in the Poly's 3's output, square plus 11A images compared to the average log perplexity between females and males. Values close to 0 indicate absence of bias. The dotted lines correspond from all occupation falls behind 9% confidence. External except bodybuilder, plumber, which the model tends to strongly associate with men. Second, we examine the level of demographic parity in the model itself. Following, we feed the image from the SLED dataset into the I3 with the chosen occupation as a prefix and record the average log perplexity score of the model generation. Demographic parity is is the difference between the average log perplexity with demographic groups and summarizes the results similar to the Pali X and Pali 3. Tends to assign higher log perplexity score to women and men across most occupations, with each difference of 37. However, fewer occupations in Pali fall outside of the interval compared to Pali X. Third, we compare the performance across all subgroups on detection class using the MIP dataset. Following again for images containing exactly a single individual, we query Pali 3 with the question, is the person in the image, and evaluate the answer on its response. Rule 9 summarizes the results. For analysis in the WebL dataset, such correlations between perceived gender and occupations. Limitations, this work is very similar to those already presented in the literature, which raises all limitations that apply to our work. Conclusion, in this paper, we took a closer look at the pre-training of the image encoder in the large VLMs specific to Pali type of by performing controlled experiments on the parrot for the first time. We clearly compare the two camps of classification, pre-training, and image text contrastive pre-training, finding that the latter can lead to better and more efficient VLMs, especially for localization and text understanding tasks. This is just one small step of aspect of VLMs, and we hope this study and results spurs the further detailed investigations of the many other aspects of training VLMs.